Welcome to the next video in the Measure Theoretic Probability series. This is video number 7.1, and in this, I'll be discussing some small examples of algebras and a very simple related theorem. So some small examples of algebras. Let's start from the smallest that we could possibly imagine, which is that omega is equal to the empty set, and it might be surprising that in fact, we can even have an algebra on this if we take the power set of omega, which in this case is just the set of the empty set. It doesn't take much work to prove that this has all of the properties of an algebra. So, does it contain the universe? Yes, because it contains the empty set, and the empty set is the universe in this example. Is it closed under complements? Well, the complement of the empty set, right? We only have one thing to check, the complement of the empty set, and that is the empty set because our universe is the empty set. And it contains that. So check, it is closed under complements. And is it closed under unions? Of course, empty set union, empty set is empty set. So it contains that, therefore closed under unions. Okay, let's take a somewhat only slightly more interesting example, which is that omega is equal to the singleton of 1, for instance. Again, we can get the unique sigma algebra defined on this omega by taking the power set. That will have the empty set, and it will also have omega. And there's nothing else in the power set. Does this contain the universe? Trivially, yes. Is it closed under complements? Well, now we have two things to check, but it's very fast. The complement of the empty set is omega, and that's there, so good. Then we take the complement of omega, that's the empty set, and that's in this collection. So good, right? We've checked everything there is to check for closure under complements, right? Each of the elements, its complement is in the collection. So it's closed under complements. How about closure under unions? Sure. Take the empty set union empty set, you get empty set union omega, you get omega, and omega union omega is omega. Okay. Let's move on to a slightly more interesting example, where this time we finally see that for a single omega, there are two different possible algebras on omega. One of them consists of just the empty set in omega. We've already run through a sort of a demonstration that that is an algebra, and the demonstration this time is no different. Also, we get a distinct algebra if we take the power set of omega. This time that will have 4 elements, but through a very similar check, we can see that that is an algebra. Although there is a much easier way to see that that is an algebra, which is to notice that what you need for something to be an algebra is a certain requirement about things that are in the collection. Well, the power set has everything. So trivially, right, is it going to contain omega? Yes, because it contains everything. Is it going to be closed under complement? Yes, because if any set is in it, its complement must also be in it because the power set contains everything. So of course it contains that. And likewise for closure under unions. Okay. Now let's get to, what is possibly the first half interesting example, which is that where we take the universe omega to have 3 things, because now we really get a collection of algebras. We have, of course, as before, the algebra containing just the empty set and omega. That's still an algebra. We have the power set. That's still an algebra. But we get some, for the first time, we get some algebras that are not one of those two. Namely, we could have, for instance, this one that has the empty set and just the singleton 1 and the set containing 2, 3, and omega. You can check that it contains omega, right? It contains the universe, of course. But then there's a slightly more interesting process, only slightly more interesting process of checking closure under complements and unions. And then we have these other algebras, and I claim, and you can try to sort of reason it for yourself if you like, that no other algebra is possible on this omega. If you leave if you want me to fill that in, you can leave a comment to the video. And if I am not too busy at the time that I receive the request, I can make a video on it. But anyway, okay. Uh, so we've kind of already seen fairly explicitly that there are always these two algebras on any omega. The one that consists of just two things, the empty set and the universe, and the one that contains everything, which is the power set. And so let's go ahead and call them the maximal and the minimal algebras. And we will prove in a minute that, in fact, no matter what omega is, they are always algebras on omega. Okay, so claim. We claim what I just said. And the proof that the power set of omega is an algebra is, in fact, right, I'm not even going to fill this argument in any more than I already have, which is just to say that because the power set contains everything, then all of the requirements that we place on an algebra are satisfied trivially, because, right, each one requires that the collection must contain this or that. But since the power set contains everything, then it satisfies those conditions every time trivially. Okay. Only slightly more work is to prove that the minimal algebra is an algebra, but you really just run through the confirmation that I've already run through for you in that first example, which is, or maybe the second example, but anyway, which is names the universe trivially. It's closed under complements by checking the complements of these two things, and then closed under union by doing this confirmation that I've already spoken out loud, and now you can see it written here. And that's it.